play.
In the United Kingdom, badminton is one of the most popular and fastest, but it would never have been so if it hadn't been for the development of these, nylon shuttlecocks. Badminton's been played for about 150 years, and the first shuttlecock could have been a few feathers stuck in a champagne cork, but the modern is a highly developed flying machine. In the skirt, there are 16 feathers trimmed to shape, each overlapping the neck. This arrangement causes the shuttle to spin as it flies. Players find it easier to see if it's spinning. Now, the central rib of the feather is narrow at the top and wider at the base. This means that most of the weight, about 80%, that's 4/5, is in the bottom half. And this gives the shuttle one of its most important characteristics. When it's hit, it very quickly turns and flies base first. The best feathers come from geese, but there's a problem. It's said that only 8 feathers from each goose are the right size and strength. So for every shuttlecock, you have to pluck 2 geese. Now, shuttlecocks don't last forever. They break, and in a top international, the players may use 20 or more. Not surprisingly, as the game became more popular, the poor old geese just couldn't keep up with the demand. Their feathers became scarcer. So the way was open for the development of shuttlecocks made from plastics materials. This was one of the first of these shuttlecocks, made in the early 1950s. It's made from polythene, which was the best available plastics material at the time. It's the same size and weight as the feathered variety, and the distribution of weight is much the same. You can see how the ribs taper as they do on the feather. But there's a problem. Feathers are very light and strong for their weight, and they're stiff. When the shuttlecock is hit very hard, the feathers collapse, but they return very quickly to their correct shape, so the shuttle flies true. Now, the polythene skirt is not stiff. If it was as stiff as the feather, it would be much thicker, and so much too heavy. And because it's not stiff enough, when it's hit hard and collapses, it stays collapsed and flies like a bullet. So that was Mark I. This next design had a smaller skirt to improve the stiffness. Well, it was certainly stiffer than Mark I, but it didn't spin like the feather, and it didn't make the right sound when it was hit. Players know from the sound what sort of shot to expect. Mark V overcame these 2 problems. The ribs were now angled, and this caused the shuttle to spin. Solving the noise problem was more difficult. This was one of the many prototypes that eventually helped to solve the problem. It copies the look of the feather, a solid top to the skirt called flashing, and gaps near the nose, and it certainly made a noise. The noise is caused when the air that gets trapped and squashed in the cone explodes through the gaps. So the prototype had proved itself, but it was no use as a shuttle. The solid flashing helped to make the noise, but it also increased the weight, and a heavier shuttle flies faster. So the search was on to make a lighter shuttle by reducing the flashing, but without losing the noise. The result? The Mark X, which became one of the first widely used polythene shuttlecocks. But development continued. Although the Mark X flew like a feather, it wasn't really stiff enough, and it was smaller and lighter than the feather. Now, at the same time that the Mark X was being developed, the designers were looking for a better plastics material than polythene, and in the early 1960s, nylon 11 appeared. Nylon 11 is a stiffer, lighter material, and this means that for the same stiffness as polythene, a shuttle could be made the same size as the feather. Now, although the new shuttle had angled ribs, it really didn't spin very well. But nylon 11 has an important property. When it stretches, it stays stretched. So the next idea was this: to stretch the nylon skirt into a corrugated, off-centered shape that helped it to spin. But this off-center stretching was technically difficult, so another way to increase spin was developed. By making holes of different sizes in the corrugations, the air flows more easily through the larger holes and causes the shuttle to spin. But on this shuttle, there's no flashing, and so no sound. Here, the flashing has been added, which brings back the sound, but increases the weight. Now, increasing the weight was important, as it meant that the new shuttle could now be brought up to the same weight as the feather. But remember, increasing the weight meant it flew too fast. The solution was to increase the angle of the skirt. This technique had been developed to slow down shuttles used in the thin air found at high altitudes. Now it was used to produce a nylon shuttle which has similar flight characteristics to the feather, the weight and so the right feel on the racket of the feather, and a similar sound to the feather. And it's more durable. It'll last much longer in play than the feather. But designers are always looking for improvements and better solutions, and this shuttle is still not stiff enough. So they tried a new shape and a new material, nylon 12. The combination of the new shape and the new material produced a stiffer skirt. But new solutions produced new problems. Although it was stiffer, nylon 12 turned out to be not as durable as nylon 11. So if you have two materials with properties you need. And that brings us to the latest stage in the design of plastic shuttlecocks. It's durable, it's stiff, it has a good sound. This aerofoil, or flap, designed into the feather shape, gives spin, and it looks good. As I said, this is the latest, but it won't be the last. For instance, it's not quite the same size as the feather. New materials and new designs will continue to be developed and tested until the day when, perhaps, the geese of the world can relax. Billy Davy, here seen in slow motion, pole vault champion. The energy from his movement down the track goes into bending the pole and pushing himself into the air. As Billy rises, the pole straightens, releasing its energy and helping to lift him high over the bar. A vaulting pole is a carefully engineered piece of sporting equipment. It's a hollow tube made from resin-impregnated glass fiber fabric. And this is what you can do with glass fiber fabric. It's soft and flexible, impregnated with resin, but before it's cooked, it's stiffer, but not yet stiff enough to make a pole. The size, the type of weave, and the amount of resin in the fabric are all important in the making of a pole. There are 50 different sizes for athletes of different weight and experience, 13-year-old lightweights to Olympic heavyweights. Two patterns, a trapezium shape called a sail piece and a rectangular shape called a base piece, are used to make each pole. A number of patterns are cut to shape before being rolled and stacked in pairs. Meanwhile, a long metal tube called a mandrel is loaded onto a winding machine. Two layers of resin-impregnated glass fiber tape are wound spirally onto the mandrel, one in each direction. These two layers strengthen the inside of the hollow pole and prevent it collapsing in use. The next stage is to wrap the base piece and the sail piece around the taped mandrel. Using an iron, the resin melts and becomes sticky, so the base piece is fixed in place. Now the base piece is too stiff to roll around the mandrel, so it's put onto these hot rollers, which melt the resin, making the fabric flexible enough to roll. As it cools and hardens, the resin fixes the fabric in place. Next, the sail piece is attached to the mandrel, and a strengthening piece is added to what will be the bottom or toe of the pole before the shape is molded on the hot rollers. Up to this stage, the resin is thermoplastic. That is, when it's heated, it softens and can be molded into shape. But now comes the change. The pole is cooked in a high-pressure steam oven for 40 minutes. In this time, the resin is thermoset. That is, it's heated until it sets permanently into shape. If we compare the two poles before and after cooking, you can still see on the uncooked pole the rough edge of the sail piece. On the cooked pole, the resin has welded, flowed, and set permanently throughout the glass fiber fabric. All the poles are tested for flexibility. First, the 0 mark is set. Then, a 23-kilogram weight is suspended from the center of the pole, and the amount of deflection is measured. In this case, 20.2 centimeters. This deflection is marked on the pole, and the pole is twisted to check that it's in the correct position for maximum deflection. 20.2 centimeters is within the range of deflection required for the rating of this pole. The final test for every pole is to check that the resin and glass fiber fabric have been correctly formed. The pole is bent to an angle of 140 degrees, which is far more than any athlete could bend it. This factory in Carson City, Nevada is the pole-making factory of the world, and you won't see a top-class or Olympic athlete without one of these poles. But you may be wondering just how far a pole can be bent. It's this degree of safety that gives top athletes like Billy Davy the confidence to reach for the sky. Tennis is another game that owes a lot to technology. The first tennis rackets were made from solid wood. A stick of ash was steam softened so that it could be bent into shape. This was a well-known technology of the time, but the racket frame wasn't very strong. 3 wood layers glued together made a stronger frame, but the wood still needed to be steamed before it could be bent into shape. But the problem with these early rackets was that the frame eventually lost its shape. It warped. And to prevent this, rackets were kept in presses. In the 1930s, much thinner layers of wood called laminates or veneers were used, and 6 of them were each thin enough to be bent into shape without steaming. Out of this shape, called a bend, 3 rackets are cut. Racket frames made from 6 veneers warped much less, and when modern synthetic glues replaced the old animal glues, the warping problem disappeared. Originally, all the veneers were ash, but ash wore away very quickly when it hit the ground. So the outer layer was replaced by hickory. Hickory is a much tougher wood than ash, but it's denser, which means that a racket made of 6 layers of hickory would be too heavy. So lighter, less dense woods, such as ash, beech, and maple, are used for the inner layers. One of the problems with early rackets was that they could break in this region known as the shoulders, which is why they were strengthened here by wrapping them in twine. This wasn't very successful, and the twine was replaced by a wooden piece known as a crescent overlay. One of these was glued to either side of the frame to give it the strength it needed. The test for the shoulder area applies a force of 60 newtons 15,000 times. To find out more about the development of the modern tennis racket, we asked a research scientist, Martin Buxton, to explain.
This, then, is the standard all-wood tennis racket. And it turns out that this head size cannot be made any larger, because otherwise the racket would be too heavy. If we try to make the racket lighter by thinning it down, the racket becomes too weak. And this type of racket was unchanged for 20 years, in the 1950s and 1960s. New materials have also been used to improve the wooden racket. For example, the wooden present overlay has been replaced by one of glass fibre in resin, which is thinner and therefore lighter and is also stronger. And when the rackets are side by side, you can see the difference in thickness. This gives a racket which is lighter and at the same time stronger. Another new material which has improved the design of tennis rackets is carbon fibre, which is lighter and stronger than glass fibre. Here we see it in filament form, and here we see it woven into a cloth. When this cloth is impregnated with resin, it produces a material which is extremely strong for its weight. Here we have a racket with a full carbon fibre lamination. This allows us to make the racket lighter by using less wood, or, as in this particular case, we can keep the weight the same and give the racket a larger head. Another use of carbon fibre in wooden rackets is as an overlay. Here we have a racket with a complete carbon fibre overlay on each side. This allows us to reduce the amount of wood, and this construction represents the lightest and strongest wooden racket which can currently be made. Carbon fibre is such a good material that naturally people tried to make rackets from carbon fibre alone. But there is a problem. Carbon fibre in resin is actually heavier than wood, and so it was necessary to make these rackets hollow.
A strip of resin-impregnated carbon fibre is rolled around a wooden stick inside a plastic tube. When the stick is taken out, the roll is fixed into a mould. The mould is placed in a press and air is pumped into the inner tube as the mould is compressed and heated.
Compression moulding is a slow and expensive method. It takes about 30 minutes to mould the racket. We had to find a much quicker way of doing it, and the one that we used is injection moulding. This is what we use, granules of carbon fibre in nylon. These are melted and squirted into a mould. The first attempt at injection moulding had a solid head section, but carbon fibre in nylon, like carbon fibre in resin, is heavier than wood, and this meant that the section had to be thin, and the racket was not strong enough. So we had to find a way of making a hollow head by injection moulding. The way we did this was to injection mould around a solid metal core. This is a solid metal core, and this is a part moulding. The carbon fibre is injected at the centre and spreads out along 3 channels to fill up the space between the metal core and the outer mould. In the final moulding, the metal core is completely covered in carbon fibre, and the injection process takes about 3 seconds. This is a complete moulding cut away to show the metal surrounded by carbon fibre. The problem is how to get the metal out. Well, this is a very special metal which melts at 150 degrees centigrade, lower than the melting point of the carbon fibre and nylon. So by heating up the moulding, the metal melts and simply runs out at the end of the racket. If we cut open a frame from which the metal has been melted out, we can see that at each string hole there is a pillar running from the inner wall to the outer wall, and this gives the racket extra strength.
The injection-molded carbon fibre racket is more than strong enough for all the tests designed for the wooden racket, and it also survives the most important test of all.
That's it.